All right, here's a fun one. Uh, a man 6 feet tall walks at a rate of 5 feet per second towards a street light that is 16 feet above the ground. At what rate is the length of his shadow changing when he is 10 feet from the base of the light? So, what we're going to have is some sort of street lamp issue thing, public safety deal, and he's casting a shadow this way. So, here's the street light. It looks like the sun, so we'll make it more lamp stylish. There we go, lamp, fun lamp shape. And this lamp is casting a shadow. Now I'm going to use some of my tools that are given to me here, but remember, from a lamp, you're going to get a straight line shadow. Light travels in straight lines. Now, inside this line, we've got a guy walking, and here's, whoops, we don't want that right there. Let's just undo that, go to this. Okay, we've got this dude walking, and maybe, it's the festive winter holiday season. Maybe this dude is none other than Santa Claus. Okay, here he is, Santa Claus, big Santa Claus, fun hat, little cool hat thing. Looks like, wow, that's really bad. Let me try again. I can do better. I can do better. Be patient, be patient. Little ball deal up there. It's all red, and he's got a snowy white beard. So here's his beard here, and a couple of Santa arms. And wow, I am not an artist, so I'm sorry. Some green gloves because hey, it's Christmas time, festive winter holiday time. Wow, I am so bad. Okay, so here he is, Saint Nick, and he's walking with his cool black boots and his little. Here we go. Here we go. He's coming together. He's coming together. Black boots, and he's walking towards the light. Don't go into the light, Santa. No, no, not into the light. Okay, just kidding. So Santa's walking towards the light, and he's walking at his shadow's changing, all this stuff's happening. Some nerd somewhere determined that Santa was exactly 6 feet tall. Now, I don't know if that's in a story somewhere and I missed it, but Santa's 6 feet tall. The lamp post here is 16 feet tall. So the question is, if Santa's walking towards the light at 5 feet per second, how fast is his shadow changing? And the question is, I don't know, but can we find out? And the answer is yes, we can. Check it out. We've got a couple of triangles here. Again, here's this big triangle. Let's call it this one right here. See the big triangle right here? Horribly outlined. Okay. And then inside it, we've got this other like bluish triangle here. See this triangle right here? There you go. Those are the two triangles that we're interested in. So let's label some stuff. I always like to label up and down Y, and we got to break Santa Claus up into a couple things. One, we got to break Santa Claus up in the distance he is from the lamppost, and then the distance for how long his shadow is. So let's call the distance between Santa and the lamppost X, and the distance from Santa to the tip of his shadow Z. And we know that he is 10 feet from the base of the light. So we know that X is going to be equal to 10 feet. Z we don't know. Now, here's the other thing. A couple other things that are really key that we need to notice. One, the rate of change of Santa Claus as he's walking. He's walking towards the origin. That's a negative number. So he's walking at negative 5 feet per second. The other thing that's interesting to note, and we may or may not need this, I don't know. The lamp post height never changes. And if something doesn't change, it has no rate of change. Now, this might come in handy if we need Pythagorean theorem, but I'm just going to say, you know what? dy dt, that's zero. It's not changing. And guess what? Santa Claus isn't growing either. So there's no way for Santa Claus to change and grow taller. So dy dt is zero all over the place. All right. Well, I'm thinking some similar triangles are what we're going to have to look at here. And so if I look at that little blue triangle, I'm looking at side Z over Santa Claus, which is a base of 6. And on that bigger triangle, I'm looking at an x plus z, that side, x plus z over the height of the lamp, which is 16. So when I work this out, I get 16z equals 6x plus 6z. And I'm going to go ahead and move over my z's, and that's going to give me my 10z equals 6x. Now, go ahead and leave them like this. You don't necessarily need to completely solve for one variable or the other, or you might want to. I mean, it doesn't matter. But the thing we're really interested in, okay, after we have all of our setup done, is at what rate is the shadow changing? At what rate is the shadow changing? Remember, shadow is z. So dz dt is really what we're interested in. So I've drawn a picture, I've established a model, I've given myself an equation. Now I'm going to take derivative on both sides. So 10 dz dt. Why dz dt? Because we're looking at the rate of change of the shadow with respect to time. And on the other side, I'm going to have 6 dx dt. Why dx dt? Again, I'm looking at how quickly Santa's walking towards the light as opposed to time. Not as opposed to time, but over time. So I know dx dt. Dx dt is -5. dz dt then remains the only variable I don't know. So I have 10 dz dt equals 6 times -5. And that's going to be 10 dz dt equals -30. So dz dt equals -3 feet per second. I hope you can see that on there. The rates, the units on this guy, dz dt is -3 feet per second. So there's I just worked out for you several different related rate problems. They're all unique. So if there's one that you would like to see, or I can take a stab at, or maybe I could get you going in the right direction, just tweet at Hazelwood Math, and I would love to be able to help you with that. These can be a little bit tricky until you figure out what's going on, but they're so cool. They really are neat and fun. And once you put Santa in anything, I mean, how can you say no? So anyway, that's it for this section. And again, practice this problem, cover it up, try it again. Can you work it out on your own or not? And if you can't, come back to the video, see where you're stuck, and then take the next step and try again.